presentation. So go ahead.
Okay, thank you, Louis. The work that I want to present here, Gaits energetic and robotic locomotion, it's part of the more theoretical work that went into my thesis that I did with Roland Siegwart at ETH. And I was looking at a number of conceptual models. Hold on. Conceptual models, as you can see them here. Conceptual from a robotics perspective, these things are fairly detailed, but they do not represent any specific robotic device that is out there. So we have distributed masses, that means we have collision losses. We have damping in the springs, that means we do not have perfect springs. There's the possibility to include a motor model in these. And they're all driven by series elastic actuators. So basically the motors are moving these discs up here, and then have a spring in between the joint and the motor, and these are basically my control inputs is used up there. So it's very similar to the actuators that Jerry is using in all his robots. Since the spring is fairly confined and can store a lot of energy, it's actually more like Mark Raybert's hoppers, where he had this big air spring where he could store a considerable amount of energy in every joint. And there are a lot of groups out there that build these robots. Jonathan has one. We have a couple of these that we showed last year in Jena. And in the theoretical work, I was looking at how to move these actuators to generate motion. And I was doing this through optimal control. That means I basically set a number of constraints that define my motion, which is basically just move forward at a certain speed and generate a periodic motion, periodic such that I only have to simulate one stride and then can do the same thing over and over again. Later on, there will be additional constraints that are added on actuator limitations, ground clearance, and so on, and then throw all this and then big optimization problem in which I minimize some cost function. An example here, it's the electrical cost of transport. And one could take the result and try to replay that on a real robot. That's not my main intention. For me, this is basically the benchmark. If I have a robotic system, a certain morphology, a certain set of parameters, I want to figure out what is the best thing I can get out of this. What is the most efficient motion that I can get out of this particular configuration. I started doing this for bipeds, or this is actually a monoped hopper or a bipedal trunking robot. And just to quickly show you that the results make sense, there are a lot of fluctuations in the energy content. So I touch down, the robot is moving downwards, being decelerated, so we're losing energy, and this has to be supported in the second half of stance. Ideally, that energy goes into the spring and is recovered. So if we look into this in terms of power, all the negative power is handled by the spring, and the actuator is only performing positive power. So this is what we would do, so it sort of indicates that what the optimizer comes up with makes sense. Interesting for me is if you now change the forward velocities, if you run this with different forward velocities, you see that there's an optimal speed, right? If I go faster or slower than this velocity, I will need more energy than at this point. Very similar to results that you would see in humans and animals. I can do the same thing for walking by telling the optimizer to have an extended double support phase. The two motions look very similar apart from the speed, but if you look closely, you see that here the springs are undergoing a double oscillation, whereas on the right side it's just a single oscillation. So we have double hump ground reaction forces, single hump ground reaction forces. That means we're exploiting basically two different modes of the dynamics in the system. It means we have two different gaits, and if we look at the energetics, again the same graph as before, we basically see that we now have two curved segments with a minimum in one of each. For running, it's less obvious that there are different gaits, but they exist. On the left side, you see a slow jog where the optimizer basically tried to keep the airface as small as possible. On the right side, you see an extended airface, and there's no gradual change. There's at some point, and we see that if we look at the energetics right here, all of a sudden it makes sense to have an extended airface, and we basically switch from this slow jog to a high-speed run. And we can do this for other kinds of motion. I don't have the time to show you them all, but in the end, you end up with a graph like this. And And I always say that my research is about the question, what implications has the meaning of Gait for robotic systems? And if you look at this, you see the answer is a lot. If I pick a certain gait, I should also pick a certain velocity, such that I'm most efficient or most efficiently using that gait, exploiting the natural dynamics in the system. If I change my velocity, it might pay off to change the gait, since at certain velocities, certain gaits are more efficient than others. And this is, as I said before, very similar to what you would see in nature. So if I compare this with the study that Hoyt and Taylor did in 1981, this is basically the same plot, right? So apart from, these are robots, these are horses, here we have the mechanical cost of transport, here we have the metabolic cost of transport, but we see the same thing. It pays off to change gaits when sweeping a certain velocity range. This graph looks a bit better because we have almost the same amount of efficiency over a larger range of speeds. And it would be nice to kind of replicate something similar in our robots. So I started looking at what does it help to change parameters. And the most obvious parameter is spring stiffness, and I did this in a very simple example, just hopping on the spot, changing the stiffness. And if you look at the mechanical energy that is used for one hop, for one optimal hop, you see it doesn't really change a lot. Very low stiffnesses are bad, but for higher stiffnesses, it doesn't really have an impact on energetics. If you include a motor model, you look at thermal losses, you see the same thing. You look at the electrical power that is used, or the electrical work that is used, you see the same thing. The only difference is that green line, and I need to explain a little bit where that comes from, that we try to minimize motor power. So limitations in the actuators, torque limits, velocity limits are of course a function of the motor power. And if you try to minimize motor power, you basically work on these constraints, which means function, if it doesn't behave numerically as well as the others, it's not as smooth. But I try to convince you that what you see here makes sense. If I change stiffness in the system, I will make the system stiffer, I will spend less time on the ground. And since I can only inject energy while I'm on the ground, my peak power will actually be a function of the amount of time that I stay on the ground and the amount of work that I need to put into. And if I combine these two, I can actually very nicely predict this curve, which tells me that it would be a good idea to build a robot with a normalized stiffness, so this is body mass divided by leg length in the range of somewhere between 10 and 30. And it's interesting to see that this is what we found by try and error if we put our robots together. This is also what you would find in nature. So some paper reported stiffness values of around 20. Bit about my ongoing research to wrap this up. So we're trying to become more realistic. So you might have noticed that the legs went through the ground, so we included limitations on this. We included a motor model which has limitations on power and velocities. And it changes the results quantitatively, but qualitatively it remains the same. So this is what we get for mechanical power without any limitations, and of course things are going up, but we basically remain with the same results. It makes sense to change gaits if you change velocity. And then I have a last slide, which is a bit food for thought. And I have to warn you, it's very preliminary results. However, what I've seen so far, everything is pointing in this direction. So what I did is, here you see mechanical work optimized and basically just limited to the stiff leg walking and the fast running motion to make sure that it's a bit clearer what we see. And now I basically did the same thing while optimizing all stiffness values in the system. So I allowed my robot to be perfect at any given velocity. And of course I was hoping for that all this would go down and it somehow tells me how to build the perfect running robot. And this is what happens. There's almost no change. And I think this is very interesting that that there's not much you can do by changing the parameters in the system, that it might not be helpful to have variable impedance in there. But to me, this is still a very, very open question. And this brings me to the end of the talk and to the questions that you might have. Both. So the last graph basically showed both. The first version was I pick a leg stiffness, and then
so in the very beginning of the simulation you were showing, I just noticed that the spring was doing nothing in all of them.
Right. That was also a sort of result that we found out, that if you have series elastic actuation at the hip, and I was wondering if the robot is using that. The answer is it's not.
So even when you have a leg mass, and you might think that it would be useful to balance the leg back and forth, you don't use a hip spring in your operation.
Right. It's a serial spring. It might be different with a parallel spring. But serial spring is basically only used to generate a certain force. So it's the actuator is moving with the leg, and at the point where the motion of the leg turns, and there you see a little bit of force or compression in the spring. Yeah.
We have a question here.
Thank you for that very nice presentation. You were thinking about cost transfer, and in a physical system you will have different sources which cause energy costs. Could you account on that? What are the major lost energy you have to account for, like impact or motor friction, or what would it be in a real system?
Where it goes. Okay, so I just had a paper presented at ICRA where I looked at different cost functions for simple in-place hopping. And what was surprising to me is that about 85% of the cost that goes into this for an electrically driven robot comes from mechanical losses, damping and collisions, and only 15% of the losses were thermal losses that come from the creation of forces. Right, so 15% forces, 85% work. Does that answer your question?
So what would you optimize in order to enhance cost?
What I would optimize, currently I'm tempted to say optimize peak power. Because if you optimize your peak power, you can build your robot smaller, you save a lot of weight, and it might eventually give you a bigger advantage than having a really big robot that is then efficient but has to carry around all these useless motors.
Time for 2 more questions. Andy?
Can you go to the slide before the first slide?
The slide before the... This one? It might be asymmetric. If you try to optimize or minimize mechanical power, it makes sense for the actuator to inject all the energy in the second half of stance. The reason for that is because you want to minimize compression forces, compression velocities in the spring, which are proportional to your damping losses. That means if I would inject energy in the first half of spring, where my spring is already passively compressed, I increase that speed, have higher damping losses, whereas if I inject all the energy in the second half of stance, I'm actually slowing down the extension velocity of the spring, and that allows me to reduce damping losses in the system, and that's why for this particular cost function, it looks different if you look at electrical cost of transfer, but for minimizing mechanical work, it makes sense to inject all the energy in the second half of stance, and that gives you the estimate.
Yeah, Andy, let's have a quick question from Andy.
You're doing optimal control with some fine grid typically with your motors. Do you have any sense of how much the shape of your curves and so on depend on the coarseness of that grid? In other words, the same way, if I get to the root of my question, you've got very low sensitivity to the spring stiffness. Might there also be sort of low sensitivity to the details of the coordination?
Oh, I tried to translate that question into my English, and then so you're asking, is it okay to have a very coarse script and you get very good results?
How similar would the results be if you did something?
So I tried basically for in-place hopping. I was using a harmonic function as input, and basically with 5 terms, you were good, and adding additional terms doesn't really help. So you don't need to be super precise for making the thing efficient. What can be, and I mean, I didn't talk at all about stability here, but if you try to make a system that is openly stable, like the work that Katja did, I think there the small details have a way bigger influence than on energetics.
Okay, thanks. Next speaker.